So I can see the screen, everything looks perfect.
Okay.
And we are started. Perfect, thank you very much. So
thank you.
Welcome and looking forward.
Hi everyone, I am Marta Passalacqua, the BIM manager of Gaia Engineering. Sorry, but today I'll be alone to make the presentation because the engineer Amaro is having another commitment at the same time. Sorry. I want to spend a few words about the company. It founded in Turin by engineer Giuseppe Gaspare Amaro in 2009. We have two locations, first one in Milan, the second one in Catania. Our work focuses mainly on fire prevention, but we also deal with construction safety, project management, and safety and security, especially during big events like Carnival of Venice or Carnival of Ivrea. Today, our presentation is about the implementation of fire prevention strategy in the BIM environment in 3 phases. Design, construction, and management. I quickly introduce the BIM. BIM is an acronym of Building Information Modeling, and it is defined by NIBS as the digital representation of physical and functional characteristics of an object. This is an operating methodology based on the creation of a single digital model in which all information relating to the building is centralized, leading from design to maintenance. Development of standards and adoption of BIM has progressed at different speeds in different countries. The introduction and adoption of this methodology has evolved rapidly in Italy over the last 10 years, beginning in the context of design and construction, and now found also in the administrative review and approval of projects. In fact, in 2014, the new directive of UE pushes member states to encourage, specify, or impose the BIM methodology as a reference standard for all publicly funded projects. In Italy, the mandatory nature of BIM took place gradually with the application of Ministerial Decree 516 in 2017. In Italy, we called BIM Decree. On the other hand, the Italian Fire Prevention Code was published in 2015 in first revision, and then published in second revision in 2019. Before the Italian Fire Prevention Code, we used the prescriptive method. This slide shows the plan of BIM degree in Italy from 2019 to 2025. The BIM methodology places its heart in the E of information. In fact, the set of information and geometric characteristics make a BIM object. In the BIM process, information is already collected from the design stage, and it is very important to have a uniqueness of data rating, and for that it is necessary to have open format file. In BIM language, this translates in IFC. IFC is acronym of Industry Foundation Classes. You can image this format like PDF. For example, if I write a text document and I use the Microsoft Word, and you usually use the LaTeX. You can read my TX file, and so I export a PDF so you can read my file. The same things happened in BIM. If I make a model with, for example, Autodescribe it, and you use, for example, ArchiCAD, you can read my model with this open format file. It is created to facilitate the interoperability between the various operators. In fact, normally architectural and structural use different software. For example, architectural team used Autodescribe it, and the structural team used Tegla. With IFC file, everyone can read the models. I show you the difference between traditional method with CAD and digital method with BIM. The first difference is about documentation. In the first case, usually we have a lot of paper documentation, of digital documentation, but we have a lot of graphic sheet, or technical report. In BIM, we have a single digital model, but it isn't a single. You have a federate model with whole models from every design team. For example, maybe you could have 2 models by architectural, or 1 model by structural, and 3 model by mechanical, electrical, and pumping team, and another model from fire safety team. The most important difference is about collaboration. In the first case, in fact, the collaboration is very chaotic. In second case, the collaboration is a very important aspect of BIM. In this slide, I show you an image taken from an article using BIM model for fire emergency evacuation plan. As you can see, we have many professional figures like architect, general contractor, structural engineer, mechanical engineer, facility manager, etc. But one is missing. This missing is fire engineer, and this figure is very important because plays a transversal role through whole discipline in all phases of the project. I talk about the Italian Fire Prevention Code. It is divided in 4 parts. First part is section G, general information. In this part you can find terms, definitions, fire safety design, and a segment of risk profiles for activities. In section S, fire safety strategy, you can find all of measures that you used to design a fire safety strategy, like reaction to fire, fire resistance, compartmentation, evacuation, etc. Section B is vertical technical rules. This section is for some subject activities. In Italy, we have 9 vertical technical rules, like offices, parking, schools, shopping activities. And the last section is section M. And in this section, you can find the methodology for fire safety engineering with 5 scenarios. If you want, maybe I passed in the chat the URL of English version of Italian Fire Prevention Code. After I passed in chat. In this slide, you can see how fire prevention engineering involves one or more design disciplines. For example, section S.2, fire resistance, involves in architectural discipline, structural discipline, mechanical, electrical, and pumping discipline, and obviously in fire prevention engineering. This is, for example, if I, the fire prevention engineer, I will say to architectural and structural team the fire resistance of walls and doors. But in the model, these elements aren't in my models. So we are working to involve this collaboration to find the better solutions to make a better model. There are many projects that we involved in BIM. For example, we used BIM to management big events like Carnival or Venice or events in Turin. We used BIM to management spaces in Roma Termini Station or management the National Cinema Museum in Turin. The others, we developed the fire prevention model. The project selected to this presentation is Gioia 22 in Milan. Is a new height rise in Porta Nuova Garibaldi. The building is comprised of 24 levels above grade dedicated primarily to offices and for underground parking levels that include technical and storage rooms. At the ground floor, there are commercial spaces that are completely independent from the office activities. In the first phase, in design phase, we made 2 models. First model is a masses model. We can say that model is a section G model. Every subject activities was modeled by mass. And in this slide, you can see the subject activities present, like the 4 underground parking levels, the commercial spaces, the offices levels, and technical spaces are at levels 23 and 24. In the project information sheet, in the property software, in this case we used Autodesk Revit, you can find the same parameters like building name, the author, activity manager, fire safety professional, main fair use. 73C in Italy are the offices, and ancillary fair use are the others subject activities. In the group of fire protection, you can find the fire prevention height, property risk, the compartment reference floor, if the activity is existing or not. In this case, is a new construction. The location of the building, a general description, and environmental risk. We used computational design in Autodesk. We used the Dynamo, and using this script to insert the parameters into the model. In this case, we use the script to insert life risk and delta A and delta occupant. These two parameters are necessary to calculate life risk. Another script is to insert in the model, in this case, to the subject activities, so in the meshes, to insert all the measures about fire safety strategy, and we insert also the parameter about activities if the subject activity is main fair use. In this case, is true because it is an office. And if the subject activity is an activity with design assessment, in this case, is true. The second model we made is a spaces and zone model. We can say that this model is a section S model, and the following slides refer to a typical floor of the building, in this case, office floor. In spaces or in zone, you can find the parameters about the measures of section S. For example, in this slide, you can find the parameters, the information of reaction to fire. And so you can find in the group of fire protection in Revit, we collected the parameters mainly in fire protection group. So you can read the parameters, the parameter of groups of materials. In this case, is GM2. For fire resistance, we have to model to insert the parameters. In the design phase, in our model, the fire prevention model, we put the parameters into the zone, because the zone represents a fire compartment. In the architectural model or structural model, the parameters is inserted into walls and doors or columns. I put properties of wall, and you can find the parameters. In Italy, we used RE 19. 19 are the minutes of fire resistance. In the design phase, probably you can find the information in the zones. In construction phase, the information it is also inserted in the elements like walls and doors, columns, etc. Compartmentation is associated to zones. You can see in the default parameters of Revit, like gross area. We added three parameters, two about fire resistance and one about maximum gross area. This value comes from Italian fire prevention code. In evacuation, you can find other parameters like crowding, occupant density, and the length of egress path. This is how we modeled the egress path. We used the railings element, and we, through the management of on a schedule, we can keep under control the length of the paths. In the symbol that we modeled of the doors, you can find others parameters to Exodus. And in this slide, you can see the parameters associated to the spaces about fire control or fire detection and alarm, and smoke and heat control. The BIM model was also used to collect all documents to apply for occupancy permit. So in this slide, you can see the model inside the CDA. In this case, is BIM 3060. And if you select a door, for example, you can find the parameters. And if you select the value of the parameters, you can open the documents. This is our Excel sheet that we use for the management of all documents. Rapidly, I talk about the IFC model. When you export from Revit an IFC model, it is very necessary to define the property sets. To management this model, especially for fire administrative, we decide to define the property sets like WWF underscore activities or WWF underscore parties involved. So I show you three examples for three property sets. First one is WWF underscore reaction to fire. If you select a space, or fire resistance, if you select a zone, and fire compartment if you select a zone. 4 examples, sorry. And the last one is WWF underscore fire control. I thank you for your attention. If you want, you write me at this mail, or you can contact me to LinkedIn. I open to answer. Sorry, to 24 minutes.
Thank you very much, Marta. A very impressive overview. So we are open for. So we have some time for questions. So I'm inviting everybody to post them in the chats if possible. We already had a first question by a case both from Polmat. Was asking if it is foreseen that this directive, 2014-24, will it become a regulation in the near future?
Yes, in Europe. In Italy, we have a ministerial decree 516. The directive is for all states of Europe. Every state, I imagine, has a technical specific degree.
Okay. And I assume that Daniel Dowd wants to ask a question. In that case, Daniel, I invite you to unmute your microphone.
Thank you. Okay, so it's kind of a two-part question. The first part is, do you have to make these models yourself? And the second part is, if not, how is it that you got this information into the other discipline models? Like, as in, how did you get the information into the architecture model and the structure model, for example?
The species model and zone models, yes, is made by me and by a team of guys. The information in others model I can't put in other models, so we are working to this collaboration because it is very important to have the information in the elements, especially because we working to read the model by administration, so it is very complicated to read the information from zone, from walls, but we are working.
Okay, that's great. Thanks very much.
You're welcome.
Okay, I don't see any immediate questions. We're almost out of time. I had one short one. At some point you showed it seemed to be a parametric way of importing data. Is that we wrote a script. In which language is the script, or which format you use?
The script use the API language. API, I think, or Python.
Okay. So it seemed similar. It was not a Grasshopper and Rhino interface. No, just checking. No, but
if you want, I pass the link of the English version of Italian version code if you want to read.
Well, definitely for some of the students present, some of them are from Italy, but others are not. So it definitely can be relevant if you can post a link in the chat. It would be great. I would now want to wrap up. There's another question in the chat, but I mean, for sake of time, I would want to thank you, Marta, for the presentation, and I invite Arjan Dexters, if you are there, to hello Arjan, to share your screen, and then we continue with the presentation from the University of Edinburgh. So Marta, again, thank you very much for a very impressive presentation.
Thank you.
And Arjan, floor is yours.
Bye.
Okay.
Hi there, everyone. Can you hear and see me?
Yes.
All right. So I am Arjan. I graduated from IMFSE in 2018, and currently I'm doing a PhD at the University of Edinburgh. Today I'm going to talk a bit about machine learning and how to use machine learning to predict the single burning item test. The presentation outline will first give some introduction about the Euroclass system, and we'll outline some key Euroclass challenges and look at how non-learning algorithms tackle these challenges. and then we'll see how learning algorithms tackle these challenges. So first things first, what is the Euroclass system? The Euroclass system is actually a model that predicts the fire behavior of construction products in the real world. The Euroclass system is based on the SBI test and some other small-scale tests. And the real-world scenario to be modeled is fire growth in a room. Because the SBI test is the most important test, the remainder of the presentation will focus on the SBI test and not on the small-scale test. So yeah, let's see how this works to go from the SBI test to the real-world scenario. So at first, the SBI test is done, and then from the SBI test, we get the SBI heat release rate. The SBI heat release rate can then be converted into a so-called FIGRA value. And to do that, you use the equation at the bottom of the screen. The equation actually states that the heat release rate value at every time step measured in the SBI test, you divide it at the time that it occurs. And the 1000 is there to go from kilowatts to watts. Once you have transferred your heat release rate curve to a FIGRA curve, you can then track the maximum FIGRA value, which you can find in the Euroclass table. And then once you have the Euroclass, you can also find the predicted contribution to fire growth in a room. Now, I should say here that the FIGRA is not the only classification parameter. There is also the total heat release rate. But for the data I'm using, the total heat release rate didn't pose any other boundaries than the FIGRA. So the remainder of the presentation will be directed at the FIGRA value. A bit more visual, it looks like this. So on the left-hand side, we have the SBI test in action. Then we get the heat release rate curve. The heat release rate curve is transformed to a FIGRA curve. For this material here, we can see that the maximum FIGRA is 450 watts per second. So then we can go to the table. We can see that this value falls between 750 and 250. So that's Euroclass D. And then Euroclass D signifies a predicted contribution to fire growth in a room, which is acceptable. So there are a few challenges to this system, and let's look at them now. The first challenge is the physical size of the SBI test. So the SBI test is much bigger than some bench scale tests like the coin calorimeter. The coin calorimeter, for example, needs a sample with an exposed area of 0.00884 square meters, whereas the SBI test needs a sample with an exposed area of 2.24 square meters. So approximately the sample size in the SBI times is 200 times bigger than the sample size in the coin calorimeter test. And this makes it the SBI test is relatively time consuming and expensive. The second challenge is that the Euroclass system often neglects the second half of the test. So on the left-hand side, we have a graph which shows the heat release rate for MDF. And it can be seen that the heat release rate at 500 seconds is 60 kilowatts. At 1000 seconds, the heat release rate is 120 kilowatts approximately. So 2 times bigger as at 500 seconds. But if we then look at the FIGRA graph for the same material, we see that the FIGRA at 500 and 1000 seconds is the same. This is because the heat release rate gets divided by the time, and thus the farther the test advances, the less significant heat release rate values become for the FIGRA. The third challenge is experimental variation. So the top 2 graphs show the heat release rate and the FIGRA on MDF for 2 different SBI tests. On the FIGRA graph, it can be seen that there are 2 different maximum FIGRA values for each test, but for MDF, it doesn't really matter because both of them fall within the class limits for Euroclass D. It gets more interesting when we look at, for instance, phenolic foam. For phenolic foam, the 2 SBI tests result in maximum FIGRA values that each result in a different Euroclass. So one test is classified as Euroclass C, and the other test is classified as Euroclass A to B. The spread becomes more visible the more tests we do. The graph here shows the experimental heat release rate of 45 different SBI tests on medium density fiberboard. And it can be seen that the gap between the 95th percentile lines for the first heat release rate peak is 60 kilowatts, and for the second heat release rate peak is 120 kilowatts. I should note here that it's not the experimental variability itself that is a problem, because that's inherent to fire testing. The issue is more how we communicate the variability to the end user, or the question that needs to be asked is whether it makes sense to grant €1 class to a material that shows a large experimental variation. The fourth challenge is whether the correlation with the real-world scenario is correct. And that is especially for any innovative materials marketed after 2002, when the SBI test became the backbone for the Euroclass system. So why are these challenges important? Why do these challenges matter to us? The physical size of the SBI test makes that the test is not efficient for product development, and this is especially relevant for the product developer. The fact that the SBI test often neglects the second half of the heat release rate data, that there is experimental variation that can result in multiple Euro classes for one material, and that we are not sure whether the SBI test correlates to fire growth in a room as outlined, makes that a Euro class on its own does not give the necessary information to make a satisfactory fire safety design. And this is especially relevant for the fire safety engineer. A possible solution for the product developer is to make a screening algorithm that's based on small-scale tests. That way, the product developer can make product changes tested in the screening algorithm. And once the screening algorithm predicts the outcome that he wants, then he can go on to do the SBI test as a validation. The solution for the fire safety designer is a more detailed ranking system. And the ranking system I propose, or the presentation proposes, is a probabilistic ranking system. So we're not going to give one Euro class for a material, but we're actually going to say the probability of each Euro class for a material. And then finally, if the screening algorithm can make these probabilistic predictions, the output can be used both by the product developer, and the output can be used as input to the new ranking system. So what will the output of such a screening algorithm look like? So here are two materials. And for the top material, we can see that the probability of Euroclass C is 19%, and the probability of Euroclass B is 18%. For material number 2, the probability of Euroclass D is 30%, the probability of Euroclass C is 9%, and the probability of Euroclass B is 60%. In the current Euroclass system, both these products will be classified as Euroclass B, so no distinguishment will be made. But clearly the materials are different, and actually material 1 might be more suited for a more critical design, while material 2 can also be used for a less critical design. So at this moment, we know what the Euroclass system is. We know some challenges of the current system. We know why these challenges matter to us. We know why they are important. And we also know what a possible solution can be. So let's have a look now at how machine learning can achieve this solution. But first, let's have a look at non-learning algorithms versus learning models. So this is a non-learning algorithm. And a non-learning algorithm, the output and input is given to the researcher. And then the researcher works very hard and comes up with a fixed correlation. The problem here is that there is no feedback loop between the fixed correlation and the input and the output, which means that whenever a new and innovative material comes on the market, the researcher has to work very hard again to update the fixed correlation. And this takes a lot of time, and that's why often the fixed correlation doesn't get updated, and therefore it gets outdated very fast. The machine learning algorithm turns this around. So for a machine learning algorithm, the researcher works a bit and makes a very simple algorithm actually. And then the input and output is given to the algorithm. The algorithm works very hard and comes up with a quite complex correlation. And that correlation is in constant communication with the input and the output. So what does that look like? If a new material comes to the market, then the new input and the new output can be given to the algorithm next to the old input and old output. And then the algorithm works very hard again and updates its correlation without interference or with very little interference of the machine learning expert. Now we know that machine learning has some benefits or big benefits even over non-learning algorithms. Let's have a look at how we can make such a machine learning algorithm. So the goal for the machine learning algorithm that I'm going to present today is that the input has to be from the concalorimeter. The output is a probabilistic Euro class. The accuracy is similar as current screening models, and the algorithm has to be flexible. The first step is that you need to source data. So the data I have consists of the materials of the 1997 Rowan-Robin study. And for each of those materials, I have 5 coin calorimeter tests. So in total, I have 150 coin calorimeter tests. The second step is that you need to import your data into into RStudio for my case. And shown here are Excel sheets of coin calorimeter results of 3 different labs. And it can be seen that the variables are named differently. It can be seen that the data is in different columns. It can also be seen that the measurements occur at different time steps. Some labs have the units at the line below the variable. Other labs put it on the same line. So this is a very time-consuming step to get this data into your algorithm. But then once you have the data in your algorithm, you can define some high-level features or input parameters. And the coin calorimeter parameters I have chosen are the total heat release rate, the time to ignition, the maximum heat release rate, the time at which the maximum heat release rate occurs, the heat release rate after 300 seconds, the total mass lost, and the coin calorimeter figura. Besides the coin calorimeter parameters, I also have some material specifications like the thickness, the density, the effective density, which actually is the density of the exposed 1 centimeter of the material, and the effective heat of combustion. The next step then is to split your data set. So the first split you do in a training set and a test set. Often it's a 60%, 40% split, but you can use whatever works for you and whatever gives the best results. The training set then is split another time in a training set B and a cross-validation set. So the idea here is that you train a lot of different models on training set B. Then with each of those models, you make a prediction on the cross-validation set. And then you can compare the accuracy in the cross-validation set. You select the best model, and with that model, you make predictions on the test set. And then the accuracy on the test set will be the best approximation of how the model will perform in the future. And the reason for having a separate test set is because the performance on the cross-validation set is a bit biased because you use it to select the best model. So the model has already seen this data, while the test set is truly unseen. The first model I made was a binary model. And this model uses only material specification inputs, like the thickness, the density, effective density, and effective heat of combustion. And the idea behind this model was that if I can make a model that doesn't require any input from any fire labs, then it can be truly used by the product developer. But because the input is so simple, I also had to simplify the output. So I put a threshold at Euroclass C, and then everything equal to C or above, I converted to a 1, and everything below I converted to a 0. So on the right-hand side, you can see that Euroclass D and E is converted to a 0, and Euroclass B and C is converted to a 1. So what this means is that the model doesn't need to predict 4 different classes anymore. The model can just predict two different things, a 0 or a 1, which simplifies things a lot. Then I wrote the algorithm, and that the algorithm told me that for my data set, only the effective heat of combustion was related to the output. The graph on this slide shows the model, and the model is actually the horizontal black line. Everything above that line, the model predicts as a 0 or Euroclass D or E, and everything below that line, the model predicts as a 1 or Euroclass A2, B, or C. And the misclassification error for this model was 15%, which is actually quite good. But then the problem is that the parameter selected by the model is just that parameter that cannot be determined without interference of fire labs. So the original idea was not achieved. But then still, starting with just a simple model is very useful because you can check if your coding is working properly and if the output makes sense. So at least now we know that the coding was done properly and the output makes sense. The next step was then to make a multinomial model. The multinomial model uses all the features and predicts the Euroclass directly. So the output is going to be Euroclass A2, B, C, and so on. The model then told me that only time to ignition was not related to the output, which is quite surprising because most non-learning algorithms available today are based on the time to ignition. But then actually when you go and look at those models, you can see that the time to ignition they use is determined in different ways. Some people say it's when the heat release rate in the cone reaches 25 kilowatts. Others say it's when it's 50 kilowatts. So they're not really using it as a physical parameter anymore. They're using it more as a parameter that fine-tunes their algorithm. So it was nice to see that that my model picked up on this. And the average test set error with this model was 10%, which was very good. And I was very happy with that. So at this moment, we have a machine learning model that takes input from the coin. The output is probabilistic. It has a similar accuracy as current screening models, but we haven't yet shown the flexibility of these algorithms. So let's have a look at that. And I lied a bit to you because actually I have a test set, but I also have a test set. So why did I do this? It's because the test set, it's not really truly unseen, because sometimes you look at it and then you make small adjustments to your model and then you look at it again. So, it's not truly unseen. But the test set is something you keep far away in your computer, and you only use it once your model is completely finished. You run it on it once, and then you have the true performance of your model, what you can expect later on. So I ran the model on this test set, and the left-hand graph here shows the 23 data points. And it can be seen that the model predicted 6 of them wrong. And the ones that are predicted wrong are the ones in the red squares. So if you then look on the right-hand side, we can see that the model predicts all the shipboard right and the plasterboard right, but it's struggling with the fire retardant Virax. So the fire retardant Virax is a Euroclass B in the SBI test. And my model is constantly under predicting that with a Euroclass D. The average test set error was 27%, which was quite bad, especially when compared to the original test set error. So let's have a look what the problem is here. This is the input from the fire retardant Virax, 30 millimeter, 2 different coin tests. And it can be seen that for the red curve, the model predicts Euroclass B, and for the blue curve, the model predicts Euroclass B. So if you look at the data that the model is given here, you can see that it's actually correct that the model makes a distinguishment, because the model interprets this heat release rate peak of the red curve maybe as a failure of the fire retardant barrier or something else, but at least it's telling me that something is off with this product. So given the data, the model is actually doing a good job. Then here is the cone calorimeter test on the fire retardant Virax 15 millimeter stick. And again, we have this peak in the beginning, and the reason why the model classifies both materials as Euroclass D. And then, but for the red line, you can see that the heat release rate becomes negative in the second half of the test, which is probably something wrong with the instruments. But still, it's very cool to see that the model also picks up on this. So it says this product is a Euroclass D because of the peak, but because heat release rate is negative during the second half, there is also a large probability that the Euroclass is B or even C. Another reason for the misclassification of the test set can be found in the input parameter, which is the total mass lost. So this graph shows the total mass lost for all my data points. The color of the data point tells the SBI Euroclass. So if you look at the fire retardant Virax, we can see that the mass lost for that material is the same as all the other wood products I have in my original database. And all the other wood materials in the original data set are classified as Euroclass D. And that's maybe why the algorithm is confused here, because based on this parameter, obviously fire retardant Virax should be a Euroclass D, but it's not. But the really cool thing about machine learning is that actually I don't need to find reasons myself while the algorithm is doing a bad job. I can just let the algorithm retrain itself, and that's what I did. So what I did is I gave the algorithm 2 data points of the fire retardant Virax together with the output for that. The algorithm then again worked very hard and updated its correlation. On the left-hand side here, we can see the old predictions. So the top 2 crosses are the data points I removed and gave to the training set. and the bottom 4 are the ones that had wrong before retraining. If we then look at the right-hand figure, we can see that after retraining, the algorithm actually predicts all 4 of the bottom ones right. So now it's predicting a Euroclass B for these 4 materials, and actually it gets the whole test set right now. So the test set error is 0% at this moment. So at this moment, we have a model which takes input from the concalorimeter. The output is a probabilistic Euroclass. The accuracy is similar as current screening models. And we have proven that the model is flexible. And this last point is what really distinguishes machine learning from current non-learning models, is that it can retrain itself very fast and very easily. And I think that's necessary in fire safety science, where we're constantly confronted with innovation. And any algorithm that cannot learn will become outdated quite fast. So thank you for listening. This is the name of my PhD. And I also put my email address there. So if you want to contact me, please do. Thank you for listening.
Thank you very much, Arjan. We have already some questions. They're a bit longer, so I will ask people to unmute if possible. If not, then I can still read it. So we have one question, for example, by Brigitte Messerschmidt. Brigitte, if you are there and able to unmute, could you say your question?
I would be happy to. So yeah, I mean, heck of a lot of stuff, Arjan, and thank you for looking at this issue. One question I just want to bring up: you show this data that you have for the MDF board, and I believe you've taken those data from the original SBI round robin. One of the challenges we had with the data, and I'm wondering if you've considered that when you're using the data. One of the challenges we had was that if you don't align your measurements before calculating the heat release, it will have a significant impact on the FIGRA value that you get. So the delay times has to be correlated. So you have your oxygen time, measured at the same time as you have your ventilation and so on, in order to have your heat release calculation work. So that's one thing, to have the delay time really adjusted. The other one is some laboratories there had not yet updated their oxygen analyzers. So the response time of those were pretty bad. And that also really impacts the heat release measurement. Did you take any of that into account in when you use these data for training your model?
So first I have to say that I'm happy to see you, because obviously I read all your papers and stuff like that, which are very closely related. So the test set, the fire retardant Ferox, is not from the original round robin. That's actually a test set I got from DBI, which did some SBI testing very recently. And then for your question, whether I looked at whether this delay time thing, I'm not sure if it's relevant for me, because I'm not working with FIGRA values per se. The only output I have is the Euroclass that's listed for the product. So I'm just having a A2, B, C, D. I'm not calculating any FIGRA and deriving from there the Euroclass. I just know the Euroclass for all the products. And then the only FIGRA I'm calculating is a FIGRA from the concalorimeter data.
All right. I was just, if the FIGRA value that you are using to train the model from the original test data, if that's not a correct one, it's not calculated in the correct way, that could give you a challenge. But if you're not using it, well, I guess it's not an issue.
Because that FIGRA is from the concalorimeter data that I'm using as input. But I will definitely look into this, because I didn't know that there was an issue with delay time for the round robin data set. So maybe for the next phase of the PhD project is going to become relevant.
Okay, excellent. Thanks a lot for that. So quite some questions still in the chat, and also other people asking to unmute. Maybe Jan or Panev, if you are available to clarify your question, that would be great.
Hello. Yes. Javor Panev from Arab. So can you first just give an example of how large were your data sets and what type of algorithm architecture did you use? And my second kind of more important question is, can you define what you refer by probability? And do you relate to that kind of epistemic probability that you're expecting to have from the process you're trying to model? For example, if you're predicting 20%, if your algorithm is predicting 20% error classification C, and I go into some lab and run these tests 100 times, am I expecting to get a classification C in like 20 times of the 100 times? Or is your definition of probability slightly different? And then does your algorithm introduces further bias in some ways to your probability measure? And based on that, how we're going to advise the structural engineer to choose its threshold to make a design judgment based on that.
Okay, so I hope I wrote all your questions down because there are quite a few there. So how large is the data set? I have 150 concoulometer tests on 30 different materials. That's the original data set. And then I have another 23 materials from the DBI data set. The algorithm I'm using is a logistic regression model, which then optimizes between lasso regression and ridge regression and elastic net regression. And there is also this lambda parameter in it to avoid very big coefficients.
Regularization. Okay.
Yeah, correct.
Okay.
Then your next question was probability. I wrote down here, but well,
yes.
What was? Can you repeat that question, please?
So the measure of probability that your algorithm is returning, how accurate is this compared to the actual uncertainty of the process we're trying to emulate? My specific example is we run your algorithm returns 20% probability for classification C, and I get those materials and I run them 100 times or 1,000 times in an imaginary lab. Am I supposed to expect that in 200 or 20 cases of those times I'll get classification C?
Well, if it depends on how much data you give the algorithm. The more data you give the algorithm, the more accurate it will be. I'm not going to say if you do this now with the algorithm that if you do an SBI test 200 times that and I predict 20% probability for C, that 20 out of 100 exactly will be C. But over time, as the model keeps learning, yes, that's what the output should be. That if the model predicts 20% probability for Euroclass C, then 20 tests out of the 100 will be Euroclass C. And then I have your last question here: how the structural engineer is going to use this data? I think that's not really part of what I am deciding here. I'm just giving the information. I'm saying that there is a problem, I think, but how the structural engineer is going to use that information depends on the structural engineer. I'm just saying the way that he is using the Euroclass now might not be giving him the complete picture that he thinks he is getting.
Okay. Thanks.
I'll do one last question as part of the series, but then of course everybody's always invited to keep on communicating afterwards. I saw a question by Davut. Davut, if you're available, you could clarify that.
Yes, it is more of a comment. I was wondering if you classify the test results into different classes based on, for example, the base material of the sample. Let's say you have plastics, you have cellulosic materials, and you divide these into different groups so that when you have a certain innovative material that is more like a polymer, then you would just only search for results or solutions or predictions in that area so that you don't get mixed up with the cellulosic materials, which would be totally irrelevant. Have you considered that? Have you tried to classify the test results based on the base material?
This is a very valid comment, and actually I had a meeting with Ruben previous week, and we said that this should be incorporated into the next model, where you beforehand you separate different materials, and based on that you go to their separate algorithms to predict more accurate results. Yes, that's definitely in our minds.
The role of the expert who is using the code, this would make it kind of more useful for the experts, but probably the more of these features you add, the more difficult it is to use for non-expert users. Thank you very much for your presentation. I think your work is really very interesting, and I wish you the best.
Thanks, David. Nice seeing you again.
You too.
Thank you very much, Arjan, for the presentation. Thank you very much, everybody, for joining us today. So I definitely invite people to continue with the questions. Arjan, there are more in the chat for you to follow up, of course. But for the sake of time, and because some people might have other obligations, I will close the official part here. So again, thank you all. And in a couple of weeks' time, we have our final IMFSE seminar of this year. So again, to both speakers, Marta, Arjan, thanks a lot. And to everybody, have a nice remainder of the day. So thank you all.
Thank you. Bye.